So let's do another problem. Here is my beam. All the loads and dimensions. I got my single-handled wrench there. And here is my beam cross-section. Notice it's an upside-down T. And this is the problem. Find sigma max in tension and compression. In other words, I have to look through the entire beam to find the maximum compressive stress and the maximum tensile stress. You have to, in other words, you have to find the point of interest. The point of interest is not given to you, you have to find it. So I will point out how to get that, but in the meantime, we have to get the reactions and draw the shear and bending moment diagram and all of that. So I'm not going to go through it. You can all convert that single-handled wrench into that and then find the reactions. You can pause the video, find the reactions. There they are. Now we're going to draw the shear and bending moment diagrams. And you can all do that. I go down 8, over, up 17.33, over, down 10, over, up, back to 0. Notice I have a concentrated moment. So I have to do more than find the areas. I find all the areas. They're all rectangles. We can get those. But when I'm drawing the moment diagram, I have to keep in mind that I have a concentrated moment. I go down area 1, up area 2, but then I have the counterclockwise concentrated moment of 20, so I drop 20, and then down area 3, back to 0. I have my beam cross-section here. I have to find the moment of inertia because I'm using this expression. So what is that? I have to get the moment of inertia. To get the moment of inertia, I have to get the centroid, and then I get the moment of inertia. So I break it up into area 1, area 2. I get my B1H1. I get my B2H2. I then multiply those out to get the areas. And then I get y bar 1. Remember, I set up my coordinate system such that it's like that. Y bar 1 is the distance to that point. Y bar 2 is the full distance to that point. And you can all figure these out. I take these values now, and I put them into this equation to give this as my y bar. Once I have my y bar, I get d1 as y bar minus y bar 1, d2 as y bar minus y bar 2. I now get these values for d. With those values for, and I don't really care about that negative sign because I'm squaring the d, so it doesn't matter whether I have a negative or not. And so I'm going to take all these values now and calculate my moment of inertia. It's there. I get that value. Okay, so I now have my moment of inertia. Now I have to find so I have that. I've got my moment diagram, and y is easy to find once we've got this all figured out. Now notice there are a couple things going on here. So I'm looking at my moment diagram, and I notice I have some negative moment and I have some positive moment. And I also observe that this is not symmetric. That being not symmetric about an x-axis means that my centroid is not in the center, and a centroid not being at the center means that the distance from the centroid to the top is different from the distance from the centroid to the bottom. So that means that I don't know, well, I have to put a lot of numbers on it. In other words, my point of interest may be here, where I have the greatest negative moment, or it may be here, where I have the greatest positive moment. I don't know. So I have to check it out. In addition, since I have both positive and negative moments, I'm bending it, in a positive manner and a negative manner, which means that my tension may be at the top or bottom, and my compression may be at the top or bottom. So I have to check out. So in order to do this properly, I have to look at this point, I have to look at that point. But then I also have to look at the bottom, and I have to look at the top. So that means what? That means that I have to, check out 4 points. I have to check out the top and bottom at that location, and top and bottom at that location. To be safe, that's what you have to do. There are ways to sort of reason it out and not have to do this, but to be safe, you need to check out those 4 points and choose the worst situation. So let's do that. So I'm going to have, for instance, at section C, so what did I say was section C? Section C is here with the negative moment. Now remember, negative moment means that my beam is bending like that. It's taking that shape. If my beam has that shape, I have tension at the top, I have compression at the bottom. And where I have positive moment, remember positive moment, I take that shape. If I have that shape, then I have tension at the bottom, I have compression at the top. So at section D, it looks like this. At section C, it looks like this. So let's take a look at it here. So I'm going to do section C. Remember, section C, it looks like that. If it looks like that, then I have tension at the top, I have compression at the bottom. And so what is my, again, I'm going to use what? Sigma is equal to minus m y over I. And so the way that I'm going to lay it out is, you fill in that blank, fill in that blank, fill in that blank. So I'm going to do this, like I say, 4 times. Top and bottom at section C, top and bottom at section D. So 1, 2, 3, 4. For all of these cases, the moment of inertia is the same. So this is the easy part. That we've already calculated. It goes in the bottom of every single one. So that's straightforward. At section C, my moment is negative 24. So, and at section D, it's 22.65. So I put in negative 24, negative 24, positive 22.65, positive 22.65. That's easy. And remember, I have my negative sign in the front of every single one of these. And then I do the bottom for this one, for instance, and I put in negative 0.1929. In other words, that's my distance here. And it's below the axis, so it's negative. I have, for this one over here, negative 0.1929 also. For the top, I'm up here, that's a positive 0.3071, positive 0.3071. That fills out all of them. So let's do the first one. I have negative, 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 so that means my answer is negative. It's compression. I get that. I have negative, negative. That means I have positive here. So there's the answer for that one. I have negative, so that gives me a negative there. I have negative, negative, gives me a positive there. Okay, so what do? I compare the negative numbers, I compare the positive numbers. So I compare that one with that one. Which is bigger? This one is bigger, so that's my maximum compression. That's my maximum compression. Now I'm going to compare positive numbers. This one is my largest positive, so that's the maximum. So we can also reason this out in the sense that, at section C, I had my negative moment, so it looked like that, so I have compression at the bottom, tension at the top. At section D, I had positive moment, so I had tension at the bottom, compression at the top. So you need to know what a negative moment diagram does and what a positive moment diagram does in terms of the shape of the beam. And you need to know this is a positive bending moment, happy face, whatever you want. Sad face is negative moment. So positive is happy, negative is sad. That's one way to remember it. But in any event, okay. So that is how we do that. You have to check out, again, you don't know the point of interest, you have to check it out. You have to determine the points of interest, and you've got to check out, in this case, 4 different points. Okay, so I want you to do this one. I've done much of it for you already. I say find the reactions, draw the shear and bending moment diagrams for this, which I've done. Got the reactions here. You should make sure you can do that. And so I draw my shear diagram up 12 over, down. I get my areas. Remember, I have my concentrated moment there, which means I have to drop down 120, up area 1, up area 2. Now, here is my beam cross-section. I have given you the point of interest. So the point of interest is here, and the point of interest is here. You need to find the centroid, y bar, I, and the sigma at the point of interest using our equation here. So why don't you pause the video, find the y bar, find the I, and then from what we've done, find the sigma at the point of interest. Okay, assuming that you've done that, here is our calculation for y bar and I, which I'm not going to dwell on, but what do? We do the same thing we always do, which is we start out with a B1H1, B2H2, and get the A's. Then I have y bar 1 is, well, that's 1 foot, so y bar is a half a foot. I cluttered the diagram up a little bit too much. Y bar 2, center of that, so the total distance here is going to be 1.05. So I now take these two, I plug them into my y bar expression. I get my y bar. I then get my d1 as y bar minus y bar 1, d2 y bar minus y bar 2. I then take my values here, put it into my 1/12 bh cubed plus d squared a, 1/12 bh cubed plus d squared a, and I get my moment of inertia. A lot of work to get the I, but we get it. That goes where? That goes at the bottom. Okay. What do I use for my M? M comes from the moment diagram. There's my point of interest. There's my value for the moment from the moment diagram, negative 24. So negative 24, don't forget the minus sign that comes from that. And then the y, and like I say, the y is the easiest thing in the world, but people mess it up. Here's my centroid at 0.5177, and then here's my point of interest here. So my y, again, is the distance from the overall centroid to the point of interest. So there's my y. You can figure that one out. It's negative because it's below the centroid, so negative 0.3177. There's the calculation to get it. Plug everything in. I have negative, 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 which gives me a negative 273 KSF, kips per square foot. So what does that mean? The negative means compression. Well, is that right? This is a negative moment. Negative moment, again, is our SAD, however you want to look at it. And therefore, I have compression at the bottom. I have tension at the top. My point of interest is below the centroid, meaning it's going to be in compression. So I should end up with a negative number for my sigma. And I do. So that's a check on it. Okay, I want to introduce a little complication here, and that is that what happens if we have what's called a composite beam, or one that's made of different materials combined. So suppose I have, for instance, wood in my cross section and steel surrounding it. So in other words, my cross section is, I have, essentially a layer of steel, a layer of wood, a layer of steel. How do I analyze this? So I'm going to propose a little lab experiment for you to think about how we would do this. Now suppose I gave you exactly this beam and gave it to you to go into the lab with it. So these are the dimensions, and this is the size, and I'm going to tell you to put a 10 kip load on it. And let's say you build this beam, build exactly this. You put the 10 kip load on it, and it deforms 0.02 feet in the middle. Say that as an example. Now what I want you to do is to create an all-wood beam. Okay, this is steel and wood, but I want you to make one that's all wood. And that performs exactly the same. In other words, I'm going to build an all-wood beam. It's going to be 6 feet long. And then it must have a depth of 1 foot. So in other words, And in other words, a couple things. I've got to use this piece in the middle. I've got to replace this steel with wood. Okay, and I cannot, this is 1 foot, I can't make it more than 1 foot deep. So, in other words, I am going to build this same beam, except instead of steel here, instead of steel there, I'm going to put wood in, and I can't make it any thicker, any deeper. How am I going to do this? And I have to make sure that I still only get 0.2 feet. And we all know that steel performs better than wood, right? So, how are we going to duplicate this? So if you think about it, there's basically, you're sort of stuck with the restrictions that I've given you. There's only one way to do it, and that is that I have to make a very large wood flange, very wide. I'm not allowed to go deeper, so it's got to be very wide. If I do that, and if I put enough wood in here, then I can get this wood to perform like this steel. That's my goal. So, okay. Now, my question then becomes, how wide do I have to make this? In other words, this could be your experiment. You start out and you put in some wood, test the beam to see if it performs well enough. If it doesn't, keep making it wider until it does. Now, why do I want to do that? Now, why am I giving you this thought experiment? The reason I'm doing that is that we want to analyze this situation, and what we're going to do, if I can build an all-wood beam that looks like that in the lab, then I can make an equivalent all-wood beam in reality and to analyze. So so in other words, I know how to analyze a beam that's all one material. We've just done it. We've just done it multiple times. So I'm going to analyze this, and instead of this, because I don't know how to analyze the steel-wood combination. So this is what we want to do. Now, I'm going to go through a little derivation to come up with that. In other words, I want to know what that B is. So how can I get that B? All right, so how do I analyze something like this? That's the question. Let's think about it. First thing I want to discuss is the emphasis that you need to know the difference between stiffness and strength. Now, you have looked at stress-strain curves. This is our typical stress-strain curve. Stress on the y-axis, strain on the x-axis. You've done this in your other classes. And let's say that you get two stress-strain curves analyzing from your materials. Just for the sake of discussion, you got one stress-strain curve that looks like this. Call that material A. Another stress-strain curve that looks like that. Call that material B. And then I ask you, which is stiffer, A or B? And I'll ask, which is stronger, A or B? All right, you have to know these definitions. Well, stiffness is E, our Young's modulus of elasticity. How is that reflected here? It's the slope, if you remember by the definitions. The slope of this curve is the Young's modulus. And what do I see? I got material A. Well, material A has a smaller slope than material B. So material B is stiffer than material A. On the other hand, which is stronger? So in other words, EB is greater than EA, material B is stiffer than material. Which is stronger? Well, the definition of strength is the peak. So what I find is that material A has a higher peak than B, so material A is stronger than B. So strength is the sigma max, is the peak. Sigma max A is bigger than sigma max B, which means that A is stronger than B. So, okay. Now we have our two materials. Well, steel is both stronger and stiffer than wood. So when I look at these two materials, this is my, I'm just sketching these conceptually. So there is steel, there is wood. Now what happens when we bend our beam, we talked about it. When we bend the beam, let's just say we're bending it like this, what do we, what are we doing? Well, if we're bending it like this, what happens? The bottom fibers are getting longer. If the bottom fibers are getting longer, that means that, that I have a positive change in length. And remember what the definition of strain is. This is normal strain, E, epsilon rather, don't call that E. This is E, that's E. This is epsilon, okay? So don't confuse those. Our definition of epsilon is delta L over L. So those fibers are getting longer at the bottom. And so if I'm looking at my beam cross-section here, what do I see? I see that's getting longer. That's getting shorter. Anything below the neutral axis, this is symmetric, so the neutral axis is in the center, where the centroid is. Anything below the neutral axis, down here, is getting longer. So let's talk about that. It's a little bit easier to envision. So what do I see? Right at the interface here. So I want to look at the bottom wood fiber and the top steel fiber here. They're both getting longer. The bottom wood fiber has the same change in length as the top steel fiber. Why? Because they're still connected. We're assuming that there's a tight bond at the steel-wood interface, which means that the change in length is the same for both the steel and the wood at that location. If the change in length of the steel and the wood is the same, then the strain is the same. Change in length, because change in length over original length. So what I'm looking at is a place where the strain is the same. If my strain is the same, I'm going to go on my two stress strain curves. What do I see? I see that I have two different stresses. In other words, at this location when this beam bends, what I see is that the wood has this stress, whereas the steel at the same strain has this stress. So the steel has more strain than more stress than the wood. The strain is the same, the stress is different. So if we look at this, we can create similar triangles. Sorry, we have two different triangles. We have that, I can look at this one here, and when I say similar triangles, this triangle here is similar to this triangle here, and this big triangle here is the same as this big triangle here. So remember, these just represent slope, right? So we've got E wood over 1, E steel over 1, E meaning the Young's modulus. So we have E steel over 1 is equal to sigma steel over epsilon. So I'm using this triangle here. And similarly, I have E wood over 1 is equal to sigma wood over epsilon. I solve this for epsilon, and what do I get? I get that, and since they're both equal to epsilon, I get that sigma steel over E steel is equal to sigma wood over E wood, which means that my sigma wood is equal to sigma steel times E wood over E steel. Or sigma steel is equal to sigma wood times E steel over E wood, either way. So I have now found a relationship. I have for instance, this ratio E steel over E wood is going to be an important relationship because it relates the stresses between the steel and the wood. So that ratio so E steel over E wood is an important ratio for us. So again, remember what we're trying to find here is that we start out with this, and I want to create my all wood beam that's going to look something like that. So I just have to get this, my goal is to get this width here. So what we're going to find is that remember, so let's just say that we've built our wood beam, and we're going to call the width W sub FW, so width of the flange of the wood, and we're going to get, notice if it's all one material, I know what the stress distribution looks like. It looks like this. It's it's our basic. It's all one material. It's what we've been doing all along. So we get a stress distribution looks like that. On the other hand, if I build steel, wood, steel, what happens? I have a stress distribution that has this discontinuity here. And why? Because we determined that at that particular strain, I had a lower stress in the wood than I did in the steel. That goes back to our, I have that strain, I have a big stress in the steel, and I have a small stress in the wood. So that particular difference is reflected in this stress diagram. So it no longer looks like that simple one there because I have mixed materials. But if this is to be the same as this, what's got to be true? The force here has got to be equal to the force here. Now, remember, in a sense, force is what? Stress times area. So here's my stress, here is my area. Here is my stress, here is my area. Notice, for the steel, I have a big stress, I have a small area. For the wood, I have a small stress, I have a big area. But it's stress times area, so all I have to do is get the same product. If I have a small stress, I need a big area. If I have a big stress, I need a small area. So what I want to make sure is that I go sigma wood times area of the wood is equal to sigma steel times the area of the wood, area of the steel. So if I can do that, then I have succeeded in doing what I want. So what do I do? What I have then is that now it's slightly complicated because I don't have a rectangle here. But bear with me, I'm going to take, rather than deal with this little trapezoid, I'm going to take, this would be a trapezoid as well, but rather than deal with that trapezoid, I'm just going to choose this little block that is the average stress in here. And I'm going to choose, down here, doesn't matter, or this one down here. It's a little average one for that little region in here. Average stress, and this is the average stress down there. So I've got these two little stress blocks. And so there's my steel stress block, there's my wood stress block. And Remember, the volume of the stress block is equal to the force. And then, for these two beams to be equivalent, the steel stress block, which is that force, volume has got to be the same as the wood flange stress block volume. So if I use T sub F as the flange thickness, and notice the flange thickness has to be the same, then I have my sigma wood times the width of the flange of the wood times the thickness. That's the volume, so that gives me the volume. Sigma thickness width, that gives me the volume for the steel. Those two have got to be the same, meaning the forces are equal. Since the thicknesses are the same, I cross those off. And I can solve this for the width of the flange of the wood. I get sigma S over sigma W times the width of the flange of the steel. And I know that this ratio, from what we just did, that ratio is equal to the ratio of the Young's moduli. So I can write that the width of the flange of the wood is this ratio, E steel over E wood, times the width of the flange of the steel. So to put this in B's, because we've been using B's rather than small w's, BW is equal to ES over EW times BS. And it's quite straightforward. So it's all about this ratio of the stiffnesses, ES over EW. So I want you to know this and memorize this. It's quite simple. We just simply take the width of the steel and multiply it by the ratio, and we're done. Very easy. So here's a simple problem. We're going to call this the transformed section. So this is important. We're going to transform the section and create our all-wood beam. So here is my original cross-section with steel and wood. I'm giving you this ratio of the Young's moduli. 30 is the ratio of E steel to E wood. Then what do I want to do if I want to draw the transformed section? I simply take B wood then is 30 times the B steel. It's 1 inch, so it's 30 inches. So my equivalent all-wood beam looks like this, where this is 30 inches, and the wood block in the center is the same. So it's that straightforward. Long description of why, but a very simple calculation to get the answer. So the whole purpose of doing this is now we're going to analyze this. We can't analyze that. We haven't learned how to do that. So what we're going to do is we're going to analyze this one, and we're going to learn a lot from that. And in the end, I'll show you what we do with it. So we're going to start out by analyzing this transformed section. So know the name, transformed section. Okay, I'm going to stop there.